Well, hello, and welcome to Lecture 4.1 for my Cognitive Psychology class at California State University, Northridge. In this series of lectures, we're going to talk about cognitive neuroscience and the brain. And in this particular lecture, we're going to focus on hemispheric specialization. Okay. In previous lectures, we've talked about the fact that you have essentially two brains in your head, a right hemisphere and a left hemisphere. Those two hemispheres normally work together, and the bridge that connects them we call the corpus callosum. Now, normally they work together, but one hemisphere can specialize more or less in a particular kind of process than the other. So while normally, again, I got to reiterate this because some people talk about, oh, I only think with my left brain. Like, no, you need both. But there are areas of specialization. I want to start by showing you that, which might seem like a curveball, but it's going to link in here, that it turns out that whether you're left-handed or right-handed changes the way you use your brain. This was a great brain imaging study that was conducted a couple of years ago, where they brought left-handed and right-handed people into an fMRI to measure their brain activity while having these people perform imagery tasks. So each subject's lying in an fMRI machine, and they're asked simply, imagine throwing a ball. So you stop and you imagine that in your head. Or imagine writing a letter. Imagine doing that. Easy peasy. What happens? It turns out that right and left-handed people use different sides of their brain to do that task. I'm right-handed. When you tell me to imagine throwing a ball, I imagine throwing it with my right hand. And as a result, we know previously that the right side of my body is controlled by the left side of my brain. In this case, the actions performed by my right hand are controlled by my left motor cortex. Well, as a right-handed person, and like the right-handed people in this study, when you ask them to throw a ball, they use their left hemisphere. When you ask left-handed people to imagine throwing a ball, they use their right hemisphere. So left and right-handed people use their brain differently. Another difference between right and left-handed people has to do with language. Normally, if you're right-handed, for right-handed people, most of the time, in fact, it's 96% of the time, language processes, or the parts of the brain that you rely upon heavily to understand language and to produce language, those sides are those processes live in the left half of your brain, in the left hemisphere. But that's right-handed people. It turns out that for 70% of left-handed people, so the majority of left-handed people, their language processes are on the right hemisphere, not the left one. So for most left-handed and most right-handed people, where neural processes related to language live varies. So handedness plays a role in where language resides. Now the question is, does it have to be that way? This is going to be a nature-nurture question. Are you always born with language processes being in your left or right hemisphere, and does it need to stay that way? Is it stuck that way? So, for example, imagine I'm a child, and a right-handed child, and I have a stroke, and it damages my left hemisphere. Am I going to have problems with language for the rest of my life? Well, that's a very important question that was conducted by another recent study where they recruited young adults who indeed had had a stroke around the time of their birth. As a result of that stroke, the part of the brain that would normally house language processes was missing. So what happens to these people by the time they're adults? In the study, what they found is when they did brain imaging on these individuals as adults, remember they had this stroke back when they were newborns, around the time they were newborns. As adults, you find that their language centers are over in the other hemisphere, right? What does this mean? It means it's a myth that any particular process or sub-process must be located in a particular place in the brain, whether a particular hemisphere or something else. Instead, the brain is plastic, and by plastic I mean just changeable. Neuroplasticity is the ability to change your brain. There are typically two ways to change your brain. One is neurogenesis, the birth of new neurons, and the other is to change the wiring or the connectivity between existing neurons. When people suffer a stroke, their brain starts to rewire using one or both of these processes. One of the things that's bad news for people my age is that neuroplasticity is strongest when you're youngest. So as you age, your ability to change your brain, the wiring in your brain, drops. And as a result of having less neuroplastic abilities, older people have more trouble recovering from brain damage. Okay. Now, while no particular process must absolutely reside in a particular part of your brain, your two hemispheres are a little better at some things than others. So your left hemisphere, we've already mentioned that. It's typically, especially in right-handed people, the site for language processes. It turns out that your left hemisphere is also a little better or a little more likely to be involved in mathematical processes and logical reasoning. Your left hemisphere also has a tendency to process information at the level of details. We call that local processing, little bits of a region or sound. Your right hemisphere, on the other hand, tends to be a little more involved in spatial perception. It tends to be a little better, if you will, at resolving spatial problems. It's also involved in an area of the brain called FFA, or fusiform face area. So the right hemisphere is typically where facial recognition occurs. And your right hemisphere has a bias or a tendency to analyze images and sounds and sensory stimuli at a global level, at a holistic, big picture level. Okay, so that's it for lecture 4.1. Come back and we will talk about split brain patients.